All right. In the previous lecture, we ended up, by the end of the lecture, we learned about the Coulomb law of failure, which ended up being an equation that describes the height and the slope of the linear envelope of failure for rocks in compression. So let's look at that just as a refresher. Let's see, okay, let's remember that equation, okay? We had that equation written as sigma c equals sigma naught plus tan phi sigma n, okay? And where each of these variables were, sigma c was critical shear stress required for faulting, and sigma naught equaled cohesive strength, and tan phi is what we ended up calling the coefficient of internal friction, and sigma n was the normal stress. And the way we ended up defining this, okay, this envelope of failure for a particular lithology, for example, if we were just looking at something like the Navajo sandstone, okay, we would take samples of Navajo sandstone and we would conduct a series of compressive strength tests, and to emphasize also that it's on homogeneous rocks, so fracture-free and fault-free rock, okay, and anisotropy, free of anisotropy, which we'll talk about later in this video, okay, and under which we have constant confining pressure applied, okay. So in other words, sigma 3 remains the same, and we amp up the maximum principal stress, sigma 1, until the rock fails, okay. And I think most importantly, though, the Coulomb failure law, it takes on much more meaning when we look at its geometric expression as plotted on a Moore diagram. So let's again remember what that looks like, because we're gonna look at more and more diagrams in this lecture. So this is kind of a little bit of a rehash of basically what we talked about in the last lecture. So let's draw just a hypothetical Moore diagram, okay, and we'll say here's our axis here. And this is positive shear stress, this is negative shear stress, this is negative normal stress axis, this is positive normal stress axis. Okay, so from deformation experiments, we end up we're able to plot and define the failure envelope for a particular lithology by marking the failure points for each experiment on a Moore circle. So recall, we would end up drawing a Moore circle, right, and look for the angle between sigma 1 and the failure plane that the faulting occur on, and plot those points on here. Again, we would end up defining our failure envelope. Okay, so again, we call this the Coulomb failure envelope. Okay, and this is essentially sigma c sigma naught plus tan phi sigma n. Okay, that's the equation for this linear function. Okay, so every point on this failure envelope line, it has an xy coordinate. So for example, here, okay, has an xy coordinate, xy, okay, that reveals the magnitudes of normal stress, which is this axis, the x-axis, and the shear stress, okay, that's on the fault at the time of failure. And in terms of the Coulomb failure law, the y coordinate is what we end up referring to as our critical shear stress at the time of fault failure. Okay, so this point here is sigma c. Okay, for unfaulted rock, we saw that part of the total magnitude of the critical shear stress required for failure is the cohesive strength here, this term up here. Okay, meaning that the rock, unbroken, fresh, unfaulted rock, has some internal strength to it that we have to overcome before we can actually form a fracture upon which to frictionally slide. Okay, so in other words, when we look at the failure envelope here, okay, when we look at the failure envelope, this line doesn't return to the origin on the diagram down here. We'll see cases in which it does here in a moment. Okay, it doesn't return to the origin. It returns up here. Okay, so it has a y-intercept. That's what this term is a y-intercept in a linear, just a simple linear equation, and or a simple linear function. Okay, and this is sigma naught, the cohesive strength. The value of the cohesive strength, again, is the y-intercept on the graph. Okay, so the rest of the critical shear stress that we have to overcome, okay, to get this side of the equation larger than this side of the equation and cause failure and a fault to form, is basically the resistance to triggering movement on the fracture. Okay, so this component is what we label, that's tan phi sigma n. Okay, and the value, it's a value expressed in terms of the normal stress acting on a plane and what is known as the internal angle of friction, which is the slope of the envelope of failure. Okay, so we saw that. Let's say we have a failure point here. Okay, so this angle here, that's phi. Okay, and just from making this into a triangle problem, okay, in order to solve QC here, right, this side of the triangle is sigma n. It's the magnitude of normal stress, okay, here, and the value of this leg of the triangle is sigma n tan phi. Okay, so the failure that it takes, or the amount of stress it takes for failure, is basically a ratio between the difference between the cohesive strength and the shear strength, or the shear stress, and sigma n. Okay, which we can express in terms of tangent. Okay, so sigma n tangent phi, and so from a practical standpoint, once we can define this failure envelope for a particular lithology, what it does for us is that it allows us to visualize the magnitudes of differential stress that are required for failure of an intact piece of rock and a fault to form. Okay, so remember the size of a particular Mohr circle when we plot it on this diagram. The radius, in other words, is defined by the magnitudes of the confining and the maximum stresses. In other words, our differential stresses. Okay, so if our differential stresses become large enough and the circle touches or intersects the failure envelope, a fault will form and the rock will fail. Okay, so say we have, let's say this is 50 MPa, 100 MPa, 150 MPa. Okay, for this particular failure envelope I've drawn here, okay, if we had a confining stress, sigma 3 was there, sigma 1 was there, confining stress of sigma 3, 50 MPa, and a maximum principal stress of 150. Okay, our circle, if I could draw a perfect circle, would look like this. Okay, and this circle does not come anywhere close to our failure envelope. Okay, so there's no orientation of failure plane that's going to form and failure going to occur. Okay, we're just not close enough to this failure envelope. Versus if I were to increase the differential stress, in other words, make there be a bigger difference between the confining pressure and the maximum principal stress, okay? And I was able to make a circle big enough. Okay, I'm not drawing this great. Just say it looks like that. No fail. Okay, whereas this circle is big enough that we started with a confining pressure of, say, 10 NPA. And we kept ramping up our maximum principal stress until we got to actually about 205 MPa, just based on how I've drawn this circle. And it's at that point the rock fails, and we can look at where the center of our circle is, okay, and wherever the tangent of our circle touches that failure envelope, okay, we're gonna read off the angle to there, okay, and this angle is 2 theta, okay, 2 theta, and we can remember, okay, the most important thing, okay, so this failed, and kind of the most important thing that these experiments showed us, and from looking at them from the perspective of more circle, okay, is we learned that the differential stress level in which a fault will form is greatly influenced by the internal angle of friction. The shallower this line is, the more flat the line is, okay, the smaller 2 theta is going to be, your theta is going to be. And the steeper it is, the larger theta is going to be, okay? And so what we learn is that the differential stress level in a fault is greatly influenced by phi, the internal angle of friction, and that in the internal angle of friction, phi determines theta, okay, which is the angle between the direction of greatest principal stress, sigma 1, and the normal to the plane. Okay, so that shows us, we can think about it just on a simple diagram. Here's sigma 1, sigma 1, and sigma 3, sigma 3. Okay, so normal to the plane is this, sigma n. This angle here is theta, okay? So theta, this 2 theta, okay? We just take half of our 2 theta here, put it in here. And then this remaining angle is what we call alpha, okay? So theta equals the angle between sigma 1 and the normal to plane. Okay, so angle between sigma 1 and the normal to this plane. And we read it whether it's clockwise or counterclockwise. That tells us whether the theta is positive or negative. So negative or positive. We can have either one, because we could have a failure plane. This is going to be a mirror image on this side, okay, our failure envelope. So we could read off this clockwise, and this 2 theta would just be negative 2 theta. Okay, this is positive 2 theta. Okay, and then alpha is what we call the failure angle. Between sigma 1 and the fault plane. Okay, so that's this angle here, alpha, the angle between sigma 1 and the failure plane. Okay, so it's complementary of theta. Again, theta plus alpha, that's going to equal 90 degrees. Okay, so that's really our most important point of all, and that is, put this on full screen here. Our most important point of all okay, is that these experiments, they basically predict, okay, that faults are going to be oriented and should be oriented systematically with regards to sigma 1 and sigma 3. Okay, and so from numerous experiments, which are shown up here, okay, we see that it's been demonstrated that phi, which is this angle here, phi, is the slope of this line, okay, the internal angle of friction, okay, it's almost universally the same regardless of lithology. Okay, you can see that this particular rock type here has a much steeper theta, but for the most part, all of these, or sorry, phis, much steeper phi. All of these phis have pretty much the same slope. Okay, regardless of rock type, and this is again for unblemished, intact rock, okay, that doesn't already have fractures in it. So for the only thing that differs in each of these is the cohesive strength, okay, where the y-intercept interacts with the y-axis here, okay, telling us the initial amount of strength we have to overcome to break the rock, its internal strength apart, okay. Therefore, okay, theta, again, is almost always about 60 degrees, okay, and therefore the angle between sigma 1 and a fault is almost always 30 degrees, okay. Let me hop back to here. Again, let me restate that, okay. Theta, because phi, which is the internal angle of friction, is nearly always, it's almost always the same no matter rock type, okay, almost always about 30 degrees, okay, and that translates from our Mohr circle telling us that theta, okay, is almost always 60 degrees, okay, and if we again think of what theta was with respect to sigma 1 and sigma 3 actually, okay, because sigma 3 is mutually perpendicular to sigma 1. This angle here, the normal to the plane, and the difference between that and sigma 1 is almost always 60 degrees. Therefore, this angle here, okay, the angle between sigma 1 and the fault plane itself is almost always 30 degrees, okay? And because on our Mohr circle diagram that we could go from the center part, we could go clockwise or counterclockwise to failure, that so essentially because theta can be positive or negative, okay, we always end up with two fault orientations that are predicted, which we call a conjugate fault set. And in our conjugate fault set, okay, the orientation of sigma 1, it bisects this acute angle between faults. And as long as the internal angle of friction is 30 degrees, then usually this angle, okay, between the two conjugate fault sets is 60 degrees, because the angle between sigma 1 and a fault plane is 30 degrees. So on each side of that, it's 30 degrees. Okay, so this acute angle is typically 60 degrees. Okay, so that this slide is just illustrating that again, because theta, okay, which is, for example, in this case, here's the normal to the plane. It's this angle between sigma 1 and the normal to the plane. Okay, this angle is alpha. Okay, because theta can be positive or negative, our sigma 1 bisects this conjugate set of faults. And depending on the orientation of our principal stresses, our principal axes of stress, we get different types of faults. Okay, so Anderson, okay, not related to me, a researcher in the 1950s, he took the Coulomb failure criteria, okay, and he concluded some general rules of thumbs about faults, okay, about the orientations of the principal stresses and the resulting orientations of fault that we can kind of follow as a general guide to how faults are going to look like in the earth. Okay, so you'll often see this referred to as Andersonian theory of faulting. Okay, and in that theory, okay, Anderson, his rule of thumb was basically that if the principal stresses or the principal stress directions are vertical or horizontal at or near the surface of the earth, okay, if the principal stress directions are vertical and horizontal, at or near Earth's surface. And what that means is simply that if we just look at a chunk of Earth here, okay, a cube of Earth, that are axes of stress are contained within the horizontal plane and are oriented perfectly vertical. Okay, or say if we had two of our axes that are in the cross-sectional plane and one is coming in and out of the page like that. Okay, and so yes, okay, these are oriented vertically and horizontally, okay, depending on whether, say, sigma 1 and sigma 3 are in the horizontal plane, and then sigma 2 is vertical, or sigma 3 and sigma 2 are in the horizontal plane, and sigma 1 is vertical. Okay, what it's saying, what it's not saying, or what's trying to make the point of, is that we don't have wacky orientations of sigma of our principal stress axes, like, you know, coming up and then poking out at oblique angles to the horizontal and to the surface. Okay, so that's part one. Okay, and given that from experiments, we seem to observe that in the internal angle of friction, again, phi, which is the slope of the failure envelope. Okay, for most rocks is 30 degrees. And given that, then only normal slip, thrust slip, and strike slip faults should occur at the surface, or should occur at or near the Earth's surface. Okay, so what that's saying is simply when that tells us, again, this really important relationship that the faults are oriented systematically with regards to sigma 1 and sigma 2. Okay, so when sigma 1 is vertical, and that means that sigma 2 and sigma 3 have to be in the horizontal plane, okay, then normal faults form. Okay, anytime sigma 1 is vertical, then we're in a normal faulting regime. And sigma 2 would be in the plane. Okay, and because of what we know about this relationship here, the internal angle of friction, okay, which tells us then that the angle between sigma 1 and theta, okay, that's going to be 60 degrees. This other angle will be 30 degrees. Okay, we can play around with triangles, but by and large, what that tells us is that this dip of this fault will always be 60 degrees. Okay, so we have this rule of thumb then that in the normal faulting regime, when sigma 1 is vertical, faults are going to dip 60 degrees from horizontal. That being horizontal ray. Got a tree up here. Okay, and when sigma 1 is horizontal and sigma 3 is vertical, then thrust faults form. And it turns out, again, that, let's extend our thing here, okay, that because of this internal angle of friction, we know generally, rule of thumb, what the dip of thrust faults should be from horizontal, okay? So when, sigma 3, geez. When sigma 1 is vertical, sigma 1 is horizontal, sigma 3 is vertical, then faults, we should form thrust faults, and faults should dip 30 degrees from horizontal. Okay, and our last type of fault, strike slip faults. Okay, when sigma 2 is vertical, which means then that sigma 1 and sigma 3 are horizontal. Okay, then and it looks like this. Just draw a road here. Sigma 1 horizontal in that direction, sigma 3 in that direction, and sigma 2 is vertical. Okay, when that's the case, we get strike slip faults. To form, and the faults should dip 90 degrees from horizontal. Okay, in other words, they're vertical. Okay, so that's Andersonian theory of faulting, just these basic assumptions and building off of the Coulomb failure criteria. Okay, we have these simple rules of thumbs. When sigma 1 is vertical, sigma 3 is horizontal, normal faults form, and the faults should dip 60 degrees from horizontal. When sigma 1 is horizontal and sigma 3 is vertical, thrust faults should form, and our faults should dip 30 degrees from horizontal. And finally, when sigma 2 is vertical and sigma 1 and sigma 3 are in the horizontal plane, then we get strike-slip fault formation. And the fault should dip 90 degrees from horizontal. In other words, they're vertical, okay? And the strike, here's the interesting thing, the strike of the strike-slip fault, okay? It's trace across the map surface, okay? It'll be 30 degrees from sigma 1, okay? So, so that's based on ideal behavior, okay? Which again, I have to emphasize here that these experiments and perfect Coulomb behavior, okay, and development of the Coulomb failure envelope, that's based on deforming intact rock that is homogeneous, okay? In other words, it doesn't have any fractures or faults or anisotropies or foliation or anything like that, okay? And would you be surprised to learn then that these natural deformation or that deformation in the natural realm often departs from predictions of these experiments, from ideal Coulomb behavior, okay? And the main reason being that in nature, okay, for one thing, once we get at deeper depths in the earth, we saw different laws take over, okay? So we depart from brittle behavior, and in nature we have anisotropy in rocks, okay? We have foliation, we have bedding, we have pre-existing fractures and weaknesses, and so on, okay? So we're gonna look at some different ways in which we depart from normal Coulomb behavior. Okay, so we're gonna look at von Mises. I'm not exactly sure how to pronounce that. Von Mises' behavior at high confining pressure. And then we're going to look at the role of pore fluid pressure. And then faulting of anisotropic rocks. There we go. Faulting of anisotropic rocks. Okay, and then faulting of pre-fractured rocks. And we actually alluded to this earlier when we talked about the strength of the crust, okay, and something called Byerlee's law. Okay, so up to now, ideal Coulomb behavior, that was the strength it took to fault a rock, to form a fault. Okay, we're going to see in a lot of ways we depart from this ideal behavior. Okay, so our first way in which we depart from our normal Coulomb behavior, which would be this part on our diagram here, were to be if we were to subject our specimens of, say, if we're again just investigating Navajo sandstone to compressional deformation at really high confining pressures, we would discover that the pure Coulomb criteria for faulting no longer holds. Okay? With increasing confining pressures, rocks begin to behave less brittle and in a more ductile fashion. Okay, so in other words, at confining pressures near the brittle ductile transition in the crust. Okay, so we saw this earlier in the semester when we looked at stress strain curves, and so just seeing how rocks deform and the linear elastic behavior, and then once we get up at really high confining pressures, that line starts to curve over, and we kind of transition into plastic behavior before the rock ultimately fails. Okay, so in a somewhat analogous manner, we learned through compressive strength tests that the linear Coulomb relationship, okay, this linear Coulomb relationship here, between fracture strength and confining pressure, it only goes so far, okay, before beyond a certain point of high confining pressure, the rocks begin to weaken. Okay, so the expression of this behavior on the Moore diagram is that the line starts to curve over in this concave up pattern and kind of flatten out. Okay, and the flattening of the envelope expresses two things. Okay, that with each increment of increased confining, within each increment of confining pressure, we have proportionally less shear stress that's required to fracture the rock in this brittle ductile transition. Okay, so the rocks are, in other words, they're really weak. Okay, and when the rocks in the brittle ductile transition do fracture, okay, we can call this the BDT, brittle ductile transition up here. Okay, when they do fracture, they fail by faults that make an acute angle of failure greater than 30 degrees with respect to sigma 1. Okay, and again, we see that, okay, by where the Moore circle intersects with the failure envelope. Okay, so with these circles here, this is 2 theta. Okay, and this 2 theta ends up being about 120 degrees. Okay, and that tells us again that theta in the Coulomb behavior area, theta is going to be 60 degrees. Okay, and that our sigma 1 will be 30 degrees, oriented 30 degrees with respect to the fault plane. Whereas over here in the what we call the von Mises failure envelope, okay, when we do our Moore circle, okay, we can only rotate this 90 degrees. That's 2 theta there, okay, which means that theta is going to be much less. It's going to be 45 degrees. Okay, so if we were to look at that, what this means really is that when the critical yield stress is surpassed, the rock will fail along more or less ductile planes that are oriented 45 degrees with respect to the greatest principal stress direction. Okay, so if we thought about how that looks here, okay, we just have let's just say we have vertical sigma 1 so that we can think about it as a normal fault. That means that our fault would be dipping 60 degrees in our Coulomb failure envelope. But over here in the von Mises failure envelope, okay, if our sigma 1 is still vertical, we're just amping up our confining pressure. Our faults are going to be at a much lower angle with respect to horizontal. Okay, so we end up with lower angle faults with respect to sigma 1. All right, so now let's look at the role that fluid pressure in faulting, or the role that fluid pressure has on faulting. So if you are in the groundwater class or you've taken groundwater, you probably realize that just about everywhere on Earth within a few hundred feet or less from the surface, okay, is saturated. The pore space is saturated in water, and as rocks get buried in the earth, the pore fluid pressure can actually even get more elevated than just simply from basically being under gravitational stresses as a simple column of water. And the geothermal gradient increases as it get deeper in the earth, okay, which can increase the pore fluid pressure. Okay, so as it turns out the elevated pore fluid pressure can play a really important role in the failure of rocks. And so 2 geologists, Hubert and Ruby, they were able to show that elevated fluid pressures in rocks tend to offset the magnitude of lithostatically produced normal stresses that are acting on a fault or fracture surfaces or within the rocks themselves. Okay, so they introduced the concept of effective stress. And you really more or less have to think about rocks actually behaving in this way everywhere on Earth rather than simple Coulomb behavior. Okay, and they say effective stress, which they note as sigma asterisk, okay, is actually sigma and the normal stress minus whatever the poured fluid pressure is. Because if you can think about it this way, if we have a fault, right, the normal stress is the stress that's acting perpendicular to a plane. And we can actually even just think about it, just any surface, okay? And if we were to zoom in on this and blow it up, right, we would see if there's any amount of fluid in here or any amount of fluid in pore space, okay, the effect that pore fluid pressure has is that it's actually pushing outward. It's pushing back against the normal stress or our principal axes of stress even, okay? So the effect is that we have to modify our Coulomb equation. So our normal Coulomb equation says sigma C equals sigma naught plus tan phi sigma n, okay? And we're going to modify that to account for pore fluid pressure. It's pushing back on all of our stresses that are oriented in the opposite direction. Let's just modify that to say sigma 1, sigma 3, okay? So sigma 1 and sigma 3, they're pushing in these directions, okay? And pore fluid pressure is pushing back against them, okay? So because we're playing with vectors, we have to account for that vector math and how that affects the total magnitudes of stress. Okay, so we modify our equation to account for pore fluid pressure as sigma C equals the cohesive strength plus tan phi sigma n minus pore fluid pressure. Okay, so let's demonstrate this. And okay, so let's just say we have just a simple column of rock. Okay, we're going to think about what the stresses are at some particular place in the Earth. Okay, and if our normal stresses are just simply from a lithostatic load, okay, so we want to know what's sigma 1 and sigma 3. Okay, we can say sigma 1, right, it just equals rho GH, okay, the density of our rock column, gravity times height. Let's say we have just sandstone, okay, which has a density of 2,320 kilograms per meter cubed. Okay, and let's say we have a column of rock that's 10 kilometers in height. Okay, so we're down in the earth 10 kilometers. Okay, so our sigma 1 is going to be 2,320 kilograms per meter cubed times 9.8 meters per second squared times the height. Okay, so 10 kilometers converted into meters is 10,000 meters. Okay, and so that equals sigma 1 equals 227 megapascals. And so let's just operate on the assumption that we don't have any additional horizontal stresses, in which case sigma 2 and sigma 3 are equal. Okay, and we're going to say we're just operating off the assumption from our earlier discussion of Young's modulus. When we compress our rock, it's going to get pushed back against. And that usually then that means this is about 1/3 to 2/3 of sigma 1. Okay, so we're just going to operate off of that assumption, which tells us, okay, sigma 3 is going to be 150 MPa. Okay, our confining stresses. So sigma 1 equals 227 MPa. Sigma 3 equals 150 MPa. Okay, So now let's think about, we're down here in the crust, right? And we have all this space that's also filled with water. Okay. And normally what we would do is we would also play this game of what's the pore fluid pressure. It's going to be rho GH. But actually we would probably have to play around. I'm trying to think about how this goes. We would have to play around with the actual volume of pore space. If I remember this correctly, but I went ahead and looked up some information, because it's not as simple as this either, just a simple column of water here. Also, it turns out that pore fluid pressure, normal pore fluid pressures that are measured in boreholes, are usually a ratio. Okay, so this is, we're going to say this is pore fluid pressure is usually, okay, a ratio of our rock rho GH, and for typical places in the crust, it's about 0.37 to 0.47, but it can get more elevated than that. Okay, and so that means that we have to take, I'm going to say pore fluid pressure is then 0.37 of 227. Okay, so our effective sigma 1, okay, after we took out the pore fluid pressure that's pushing back against everything, is 143 MPa. And our effective sigma 3 is 66 MPa. Okay, again, just thinking about this up here, right? This is pore fluid pressure, okay? And it's going in the opposite directions that our sigma 1 and sigma 3 are. So to get effective sigma 1 and effective sigma 3, those equal sigma 1 minus the pore fluid pressure, and sigma 3 minus the pore fluid pressure. Okay, so that changed our total magnitudes of sigma 1 and sigma 3. But it turns out our differential stresses are no different. Okay, in both cases, the differential stress is 77 MPa. Okay, so let's think of the significance of that in terms of our Mohr circles. Okay, so I pre-drew this sigma n, sigma s. Okay, so originally we had sigma 1 equals 227 MPa, and sigma 3 equals 150 MPa. Okay, and let's just say hypothetically, here's my failure envelope. Okay, so let's plot this on my Mohr circle. Looks something like this, right? Okay, so sigma 1, sigma 3. Okay, and the difference between the two is our differential stress. Now, this does something to our Mohr circle when we take the effective, when we account for pore fluid pressure. It doesn't actually change the size of the Mohr circle, okay, but it does move, it shifts the Mohr circle closer towards failure, okay, because the differential stress never changed. We just took away the pore fluid pressure from sigma 1 and sigma 3. Okay, so our effective pore fluid pressures were now 143 and 66 MPa. Okay, so 66 about right here, 143 about right here. Okay, I didn't draw this great. So what it did was it shifted our Mohr circle over closer to failure. And if I drew this differently or more properly, maybe we would see that it shifts us closer to a failure envelope. Okay, so adding in pore fluid pressure can actually result in other words, faults end up forming at much lower stress levels than they would normally predicted if they were dry and we didn't have pore fluid pressure pushing back on everything. Okay, so we'll talk about what was next. We'll talk about faulting of anisotropic. We're going to take a break in this video in part 1, and we'll talk about anisotropic rocks and faulting of pre-existing rocks, and then we'll actually get into talking about thrust faults.